So coming back to the point that what are the things you already means the voltage is very important quantity at the substation level. It impacts your overall power transfer. You create high voltage system so that you can produce means you can send large amount of active power from one place to another place, because means at lower level the amount of current will be very high for transfer of same amount of power, which is not justifiable or it is not technically possible. Also you will have to do a lot of investment in that direction, while if you do the same thing at very high voltage level, the same amount of active power transfer can be done in a very cost efficient manner. So that's why we preferably generate at low voltage, transmit at high voltage, absorb at low voltage is there. So you generate all this transmission at higher voltages. So whenever we are doing this transmission at higher voltages, then higher voltages also has its own kind of challenges. So what kind of challenges is being observed by the system? So already I told you means that different voltage level are there, like 400 is there, right? 220 is there. So we have all your equipment designed at these rated voltages, right? So whenever you don't maintain the equipment at these rated voltages, it will have a stress on the equipment. So your equipment will get a stress, life will deteriorate, and also it impacts the, means the safety of the equipment as well as the safety of the human life also at those places. So that's why it is very important to maintain the things in the well within the limits. So this is one of the job that operator has to do all the time. Okay. So what the operator has to do, maintaining the voltage at bus within the acceptable limit during peak and off peak hour. Okay. So it is not that I as informed you that let us say this is the power that is being transferred. Okay. So let us say it is a 24-hour duration. So in the morning, the active demand is less. So it is like this. As soon as you start moving into the daytime, the power flow on this will increase this transmission line. Then certainly at the evening peak, again it is increasing and night is again reducing. So this is the power flow on this transmission line that is happening throughout the day. Based on this power flow, how much is the reactive power that will be generated? It will be decided for this transmission line, right? So if your transmission line is not loaded at its optimal loading, then it will be either producing a reactive power or it will be absorbing the reactive power. So how it is being done? So we have already know about our term called SIL, surge impedance loading, right? So omega L is equal to 1 by omega C. Okay. So at what happens is that at surge impedance loading, your reactive power generation is not there. Okay. So you have optimal reactive power, means the line is at the optimal voltage level. You don't have to worry about the voltages. However, if you have this loading, surge impedance loading, if it is loaded beyond surge impedance loading, the voltages will go down. And if it is loaded above surge impedance, lower than surge impedance loading, then your voltages will go up throughout the transmission line. So if this kind of thing happen in the transmission system, because your day-to-day power flow on the same line will be varying all the time, right? Depending upon the load generation balance in the system. Your how much load is coming into the system, how much load is going out of the system. So this power flow always varies. When this power flow varies, then reactive power generation and absorption by this transmission line will also vary. And if these vary, this will also directly impact the voltages of these individual nodes or the substation through which these lines are getting connected, because there the active and reactive power, the reactive power variation will be there due to the load change in the loading of the transmission line. So during the low loading, there will be high voltages you will be facing, and during the high loading, you will be facing low voltages. So here you may face low voltage into the system. If the power is like that, and let me assume that it is the 400 kV. So what will happen is, and it is, let us say 1 per unit voltage, 1.1, and let us say it is 0.9. So when it is at optimal loading, so what will happen is that let us say this is the optimal point, optimal loading, this particular P. So here your voltages will be like this. Here you are operating at this. When your voltages is on the lower side, your operation will be like this. And when operation, this is like this, your voltage is reducing, and this is the voltage part. Okay. So what is happening is that as the reactive power is active power is changing into the system at different operating points throughout the day, the voltage of that node is also the substation node or the in terminal node is also varying a lot. And due to that, you have to, and for the safety of the system, equipment safety, all this safety aspect, as well as to operate the system within the limit transmission line limit and to safeguard the entire system, to maintain this voltage within the limit. So there are operational limits that are defined in which you have to maintain the voltage. So that is the job of the grid operator. However, grid operator can only do his part when the proper planning is there. He has been given adequate resources to maintain this reactive power. Unless until you provide those kind of equipment to the reactive power or the reactive power resources to the operator, he will not be able to maintain on its own. He can only then there will be a chance that he will be operating out of the limits. Okay, out of the operational limit, out of the acceptable limits also. So those will be a vulnerable situation for the operator. So we need to have a very good planning. In the operation side, there is a good flexibility for the system operator. So the challenge, the first thing is that you have to maintain the voltages within a acceptable limit during the peak and off-peak power hours. So during different duration of the loads, you have to maintain the voltage at this 1 per unit, near to 1 per unit. Difficulties in transferring reactive power over long distances owing to high losses, right? So we can't transfer the reactive power through a long distances. Okay, you have to do it at means you have to do all this compensation at local level. So for the maintaining the reactive power through, let us say 5 nodes are there in the system. Okay, so here V1 is there, this V2 substation, this is V3, V4 and V5. So if you have to maintain the voltages of this node, let us say V2, you provide some reactive power support over here, most of the reactive power support over here. You may provide some of its reactive power support from this point and some of the reactive power support from this point, very small one. But you don't want that your voltage is this one and you want to control the reactive power from, let us say, this V6, which is quite located quite far away. Because moving of this reactive power means, because for movement of this reactive power to balance this power, what you need to do, I have informed you that V1 greater than V2. Then the reactive power will flow from the higher voltages to the lower voltage. The reactive power will be like this. Okay. So assume that, okay, just assume that this is operating at 0.6. Okay, this point. This is 0.8. This is 1.1.1. This is 1.2 and this is 1. So just tell me whether you will be able to transfer reactive power M bar from this part to this part. No. Reactive power will go from 1.2 to 1. It has the direction of flow. For maintaining, if you want to transfer this reactive power from this place to this V5, which is at 1.02, you have to increase the voltage of this point above 1.2 so that at this point you can transfer the reactive power into this direction. So that's why, again, coming back to this, this will be able to transfer the power to this side. Let us say if it was 0.8, while you have to control the, let us say, and now again, let us make it 1.2. Again, there is a problem of reactive power. High voltage is there. So for maintaining the high voltage, if you want to control, if you reduce the voltages over here, certainly some reactive power will flow from this direction to this direction and it will get absorbed here, but the control will be poor. However, if you do the reactive power absorption at this point itself, it will be much better absorption of the reactive power and your control will be very good. Okay, just let me. Yeah. Then the variation in demand pattern, voltage profile during different seasons, specific event, festival, load crash. So already many of you have already I discussed that the overall throughout the day, this voltage pattern will be different. Demand pattern will be different. Depending upon that demand pattern, voltage profile across the different nodes will be different. And these voltage demand pattern will vary according to different seasons, right? So you have seen that in the winter you are facing high voltage, while in the summer you faces low voltage. Because in the summer amount of load is high and in the winter amount of load is low. However, in many portion you also see that due to the means this heaters basically. So when the heaters, a lot of heaters are coming into the winter, then there also we face a low voltage situation. So these kind of issues are also, and during the specific event festival the pattern is also different, right? So, and you can also face that there is a sudden rain is there. So suddenly what will happen? Distribution company will start tripping the loads and you face a severe high voltage during those kind of conditions when the distribution company trip the loads directly. So in those situations, we face a severe high voltages. Many of the transmission line trips on the high voltage situation, a high voltage protection. So that's what we call as a load crash in the system. It is not that the consumer are switching off the load. It is basically when the distribution companies are switching off the loads to safeguard the human life itself. Okay. So that there is no electrocution or short circuiting, all those kind of things. However, in those situations, we face load crash and high voltages. Then this one is hmm, avoid maximize or avoid or minimize the tripping due to over voltage and overflux. So we wanted that your transformer, if it is operating at very high voltage and low frequency, then VYF protection is there to protect it because there will be a very high external force in the winding of the transformer. So this will result in deterioration of the or the means alignment of the transformer itself. So that is a problem with the transformer. While the transmission system, you can face a over voltage kind of situation which will stress your different equipments connected to the transmission system. So that's why you have over voltage and over flux protection in the system, and the job of operator is that to avoid these operation which are basically meant for the when you face some severe contingency in the system, not for the day-to-day operation. You wanted that line should trip on over voltage or there should be overflux tripping of the transformers. And another thing is that with a high RE generator, we will discuss the over voltage issue related with the RE generator or the active power issue related with the RE generation with the RE class basically. So just assume that there are issues related with the where the pool of REs are getting connected. The fault level of that substation is low. Strength of that substation is low. So any kind of fluctuation in reactive power at those places result in severe variation of the voltages. So this is also acting as a challenge for the operator to maintain the voltages and to reduce this fluctuation in the system so that RE generators do not get impacted. So these are the challenges. So what is the means overall the challenges? What is the repercussion of those challenges onto the system? So there can be we call transform it as a voltage stability in the system. We have already discussed those voltage stability in the previous slides. So we will just look at that what how means we define these kind of terms basically. So the thing is that power system is basically planned to operate within a range of voltages. So you have two real limits, operational limits and emergency limits. Okay. So you have emergency limit is that it is for the human safety, equipment safety, and operational limit is that you maintain because there is a continuous rating for any equipment. Okay. It is not that any equipment is rated to operate at 400 only. Yeah, one per unit. It is rated to operate within a band of range. Okay, plus minus 5%, let us say. So this is my operational range in which let us say 1.05 to 0.95. So this is the range in which I have to operate the equipment. So this is my operational limit. So the various operational limits for each voltage level has been defined in the CS standard as well as the Indian electricity grid code also. Okay, so we will look into that in the later slide. But in general, it is for 500 K, so 400 kV, 765, it is generally plus minus 5%. Okay, while the 220 kV system, if you see, it is plus minus 10%. Okay. So that's the operational limit. Emergency limit is that beyond which This is basically emergency limit. You don't want to go into the system, into the emergency limit. Emergency limit is for the safety of the equipment. So you don't want to encroach into the emergency limit. If it is getting encroached, there is a limit, there is a threshold, there is a time bound threshold that has been provided so that in case it is reaching this emergency limit, you need to switch off the equipment. So that is the limit that has been prescribed for different equipment. So these both voltage limits and the operational emergency limit are defined in the different standards in the Indian power system. So what is voltage stability? It is the ability of any power system to maintain the steady acceptable voltage at all buses under normal operating condition and after being subjected to an event. So normal operating condition as well as any after any event. So in Indian power system, we consider one event as n-1 condition. So whenever there is a tripping of one equipment, one transmission line, then also your voltages should be acceptable voltage limit. And what is that acceptable voltage limit? It is being defined by the operational limit. So your voltages should be within the operational limit without doing anything, any kind of changes in the system. Let us say one transmission line trips, still your voltage should be within that operational limit. That's the criteria that has been provided. So we will look into those things. So how means this for the maintaining voltage of sending as well as receiving in for required active power, we have already discussed this in equation. So how we will see that what kind of things happens when there is a changes in the system loads, whether when the load increases, when the load reduces. We already know when if you increase the load in the system, your voltage is going to reduce because the transmission line loading is going to increase. And if the transmission line loading is going to increase, it is going above surge impedance loading. What it means, it is trying to absorb more reactive power, and therefore you have to infuse MVAR into the path. You have to increase the voltage for the same amount of power transfer. You can easily look from this equation itself. While same load reduces, voltage increase, decrease in MVAR across the path, then you have to infuse the, if when the load reduces, then you have to absorb the reactive power from the system. You have to put reactor into the system. And what is voltage stability? We have seen that maintain the voltage within the limits during any normal condition as well as any event. While instability refers that a system enters a state of voltage instability when a disturbance, increase in load or system changes causes the voltage to drop quickly or drift downwards. Okay. And operators and automatic control fails to halt that decay. So if the voltage is going, let us say this is the voltage. Okay. So if it is reducing, then you are not able to control this reduction in the voltage. Okay. And it goes down, it collapses. So this is what you are not able to have. You don't have enough control over the voltage decay during any kind of changes in the system, increase in the load, or any kind of event or any drift is happening in the voltage due to the change in the entire load generation balance or any contingency. So you will face such kind of decay in the voltages, and it will collapse. If the decay continues unabated, yet is not being controlled, then you will face either the steady state angular stability or the voltage collapse. So why I was telling you that in the previous equation, I was telling you that this, if you don't control the voltage and if you transfer the same amount of reactive power, if it is going down, then this particular point for this maintain the same power transfer, this angle will start increasing from the load to the from generation to the load center. And if it goes on increasing, then you already know that your operation is like the swing criteria, swing equation is like this, right? So this is P and this is delta. If you are operating here, let us say sine 15 degree, sine, then again the voltage is reducing. You want to transfer the same amount of power. It is going to 30 degree, 40 degree, 45, and then 90 degree. And after that, if you want to transfer any amount of power, it is going to get reduced, means active power will reduce. So what will happen? You enter into the state of instability. Your system is not able to maintain the voltage. Your generator is not able to maintain the voltage. Its load angle has already reached its own limit. And if you try to infuse any more amount, if you reduce the voltage any further, immediately the generator will go out of out of a step basically. So you basically go out of synchronism and there is a voltage collapse. When generator go out of synchronism, then there is no generation in the system. Voltage will start decreasing and there is an immediate collapse that will happen into the system. So this voltage decay may just take either few seconds or 10 to 20 minutes. It depends wherever at what point you are lying and whether, let us say, if you are lying at this point, okay, and if increase load at, let us say, load is increasing swiftly, it is further increasing, the load is increasing, voltage is decreasing in this way. So as soon as you reach this point, whatever we call it as a knee point or knee voltage, at this point, what will happen is that your generator, whatever the reactive power sources into the system, that will not be able to now sustain the transfer of active power into the system. That is not there. The electromagnetic force that was required to hold the system, that is at its own limits. So at that point of time, if you try to further reduce the voltages, there will be immediate collapse in the system. All generator will be going out of a step. They will not be able to sustain the reactive power into the system. So this kind of things has already happened in the past in India due to the there have been a cases of voltage instability in Punjab system. So that's why its ATC TTC was further calculated separately. So what kind of things will result in the what are the issues that we are going to face during the voltage instability? Loss of load or some buses or some substation or by loss of any particular area itself. Then tripping of transmission line, cascade tripping can also happen due to the loss of voltage. Why this voltage instability is very dangerous in the for the transmission, particularly substation people, transmission people. Why it is happening is that, let us say if voltage is zero, so all whatever the relays that will see, it is basically it is V by I, apparent impedance it is absorbing. If the voltage is getting to lower value, then what will happen is that your apparent impedance will encroach into the protection zone. So this will happen, result in the operation of the different kind of relays into the system. So this is one of the problem that we face during the voltage instability. Many of the transmission protection can operate during that situation. When there is a voltage collapse, we have seen that I just let me share one example. There is a transmission line 400 kV. It was a long transmission line like this was there, 400 kV, and there you have 132 kV transmission system. Okay, so let me create this. This is 400 and this is 132 kV. Okay, this is northeast example. And this was feeding a kind of, radial load into the system. And this is again, it is here, it is connected like 132 kV itself. However, you have a very good voltage source. This is a generating plant. Okay. So everything is good. 400 kV supporting the system and the power was transferred from this place to this radial load. What happened is that this particular ICT got tripped. Okay, whatever there was a problem in the system due to which this 400 kV support went out from the system. So what happened with the system, or what was the exact situation for that particular system is like this. Now the entire power has to transfer through this particular 132 kV network to this place. And this was not a feasible situation, right? Why? The impedance was very, very high. So very high impedance, if you want to transfer that much of power and there is no reactive kind of support, very long 132 kV line, then you know that P is equal to V1, V2 by X into sine delta, right? If you have, let us say it is 1 per unit, X is very high, what will happen to this V2? If you want to try to push that much of power, right? So what will happen is that this V2, somewhere this V2 will go zero. So this is what voltage collapse will look like. When you are not able to provide that much of reactive power support in between, then there will be a voltage collapse at in between any point, and there the V will be zero. And there what will happen is that its distance protection will start operating. So this is the situation that you face during the voltage instability. And again is that some generator owing to high field current, because voltage collapse means you have to inject very high reactive power to maintain that voltages. Okay. So that may result into the very high field current, and that can result into the overcurrent relay in the AVR also. That may also operate for protecting the your field circuit basically. So that is also one of the problem that we face, voltage instability. So there are kind of two kind of voltage stability problem that we can face. One is the voltage stability problem, that a small disturbance. Another is large disturbance. A small disturbance, I told you that let us start increasing the load one by one. The load is increasing and go on increasing, and you don't have that much of reactive power support into the system. So then this voltage collapse or voltage stability situation will be gradually coming into the system. So that's why a small disturbance, voltage stability. While large disturbance happen when you have any fault, you need loss of generation or tripping of heavily loaded transmission line, those kind of situations, sudden it is happening and it is creating a very large voltage changes into the system. So in those cases, this will be this will be called as a large disturbance voltage stability. One thing we should know that whether it is a voltage stability, whether it is angular instability, whether it is frequency instability, any one of them can encroach in the other area and result into the other kind of instability problem. Let us say load generation balance kind of issue. Okay. So if there is a significant load, frequency will go down. If the load is very high, then there can be a situation that many transmission line will be overloaded, due to which their voltages will be low. And at the same time, if the voltages are on the lower side, you are pushing the power, same amount of power you have to transfer, then your angle sine delta P is equal to B1, B2 into sine delta by X, that sine delta will be high, right? So you are facing frequency problem, voltage problem, angular stability problem at the same time. Which one will trigger first? It depends upon the triggering value, which one is near in a stability limit, whether it is nearer to the frequency in a stability limit, where it is nearer to the voltage in a stability limit, or whether it is nearer to the your angular instability limit. So either of them can hit first. But certainly there we are going to face, means after first limit is hit or any tripping happens, then subsequently other instability lead to, and all other kind of cascading, everything will come together and fall in place, and this will result in a very significant kind of disturbance into the system. So that's why it is very important to avoid this voltage stability problems, instability problems, because it will help us in avoiding blackout and voltage collapse. So why means what kind of issues that we have is that our generator is located on this end, and there is a significant amount of transmission line in between, and there is a load at this end. So our load centers are there and generator centers are located quite far away. So this is one of the challenge that we as a system operator faces. So you have to provide adequate reactive power support between the load and generation, between the all these substations, so that the voltages can be maintained and you are able to transfer that much of active and reactive active power safely into the system from the generation to the load center. And we have lower number of voltage control, right? The voltage is where the voltage can be controlled. Either it can be controlled at the generator or it can be controlled at the any kind of fax devices like STATCOM or SVC synchronous condenser is there. There you can control the voltage through the active power, dynamic active power control. So for controlling the voltages, you need to have a very dynamic active power control, reactive power control. For that, if you have a generator or you have a fax devices, that you can do it. Otherwise, it will be varying depending upon the power flow that is happening into the system, or the how much the active and reactive power compensation that has been provided, or it has been switched on or switched off at that particular node. So it will keep on varying, except the generator and the fax devices substation. Otherwise, there means where you are able to control it. So what you know that there is a very large number of substations are there, but generating stations are limited, fax devices are limited. So that's why it is very important that we need to consider during the voltage stability how many voltage control buses are there in our control, because for those substation generating plant, you can ask them to control the voltages, you absorb the voltage or inject the voltages. Then there is another issue is that capacitive shunt capacitor. So in many times the challenge is that you have to optimally utilize the shunt capacitor. When the voltage is when the loading is high, you have to switch off those shunt capacitor at the loads, and when the loading is low, you have to sorry, when the loading is high, then you have to switch on the shunt capacitor to provide them reactive power support, so that those loads can operate at unity power factor. And when the loading is low, load is low on the distribution side, you have to switch off those capacitor. Otherwise, what will happen? You will increase the your means the you are not operating at the optimal this unity power factor. This will be injecting reactive power into the system, resulting into the high voltage and first at the distribution level. Then this will start when the your distribution level voltage is low, the LV side of the transformer voltage is high, and the HV side transformer voltage is low. Reactive power will start flowing from the LV to the HV side, and then goes on. So your reactive power from the shunt device or lower voltage distribution system will start flowing into the transmission system, and it will increase the transmission voltage also. So this will result into the problem into the percolation, and means the whatever the origin of the problem was at distribution level, but it has extended to the transmission level. So that's why it is very important how to you means extend means utilization, proper utilization of shunt capacitor into the system by the operators. Okay. So the other things are also there, like whether system is operating any near limit, or whether there is an outage of many important generating plant which was controlling the voltages. So if there is no these kind of things are there, then we have to properly plan how we are going to control the voltage in those areas. So these